So today we discuss generating functions for random walks. So as we saw last time, many problems in random walks can be solved by using combinatorial arguments or just counting the number of paths. However, if we consider, say, a random walk as, again, is defined in this way, with S0 is equal to 0. But now let's just assume that each step has probability +1 is in positive direction with a probability P, and the probability that xi is a negative direction is -1, xi is -1 is equal to 1 minus P, and this we will call it equal to Q for notational convenience. Okay, so now if P is different from 1/2, then so for example, if P is larger than 1/2, then the paths that are going that are increasing, that are going upward, they are going to be more likely than the paths that are going downwards. In particular, if you take a particular path, which is a sequence of n steps, then the probability of this path will be equal to P times the number of steps up, which is Sn plus n divided by 2 times Q times the number of steps down, which is n minus Sn divided by 2. So you see that different paths, because Sn is a random variable, depends on omega, so you see the different paths will have a different probability. So this means that we cannot no longer use just counting problems. We cannot just count paths, because paths have a different probability. So we cannot use the ideas that we have used in last lecture to compute probabilities of random walks. Okay, so what we can do is instead use generating function for this case. And let me discuss this by first analyzing the problem of the waiting time for a gain. Okay, what do I mean by this? Well, you can think that this problem is the problem of a gambler that plays repeatedly the same game, and each time either he wins one, say, euro with probability P, or he loses 1 euro with probability 1 minus P, which is equal to Q. Okay? And then what we are interested in is the total gain of this player, of this gambler. And we are interested in the event where so in the event that he has a positive gain at time n, so this is the waiting time for the first game, and this is the event that Sk is non-positive for all k which are between 0 and n, and that Sn is equal to 1. Okay? So if you want to, we can plot a trajectory or particular walk that contributes to this event. So it will be something that goes like this, and then at time n is Sn, time n, you have, so this gambler gains €1 for the first time, okay, or say his total gain is positive. Okay, so we call phi n as the probability that t is equal to n. And then what we can do is to build a generating function of this event, of this probability. And this is the expected value of s to the raised to the power of this random variable t. Okay? Now, using generating function, it is very easy to solve this problem. And the idea is the following. So, let's analyze the first step, what happens at the first step. So, with probability p, so the first step goes in the positive direction. So you have a first step, you have a gain just at t equal 1. So with probability p, then the time you have to wait is exactly 1. Then what happens with probability q? So with probability q, instead, you go down by 1 step. Okay, so then what you have to do is to wait the first time, let's say t1, where you go back to 0, and then a second time t2, where you get from 0 to 1. Now, so you can write that your t is equal to 1 plus t1 plus t2. Now, you can split this expected value in these two events. So with probability p, you will have just the expected value of s to the power 1. And with probability q, you have the expected value of s to the 1 plus t1 plus t2. Okay? Now, the main insight is that if you look at what is the distribution of t1, well, this is exactly the same problem as this, because it is the time you have to wait to get a gain starting from this point here. Okay, and again, this is also a problem, a random variable which has exactly the same distribution, because it's the waiting time for the first gain starting from this point here. And because the random walk in this time interval is independent of the random walk in this time interval, T1 and T2 are independent. So summarizing, we have said that T1 and T2 have the same distribution of T, so they have the same generating function, and T1 and T2 are independent. So this allows me to simplify this and to say, well, this is P times the expected value of S is just a constant, so this is just P times S. And then we have Q times S to the 1 is just S. and the expected value I have the expected value of s to the t1 and the expected value of s to the t2 because they are independent. But then each of these has the same distribution as t, so its generating function is just given by phi. So and then we have that this is equal to phi, this is equal to phi, so this is phi squared. Okay, so now you see we have an equation for the generating function, which is a quadratic equation, and we can solve it. Okay, so the solution of this quadratic equation is very simple, and it's 1 minus square root of 1 minus 4EQS squared divided by 2Q times S, because QS is just the coefficient of this. Okay, so notice that when I solve a quadratic equation, I get two solutions, and I have to choose the one which is consistent with the property of this problem. So one of the properties of this problem is that the probability that t is equal to 0, phi of 0 must be equal to 0, because there is no probability that you get the first gain without even playing. And so this implies that phi of 0 is equal to 0. So this solution here with the minus sign is the one that satisfies this requirement, because if you take the limit as s goes to 0 of this, you get 0. And whereas the other solution, which would have a plus sign, does not satisfy this condition. Okay, so now given the solution for the generating function, so let me write it up here. We can get a lot of insight from this. In particular, well, in this case, well, first of all, we can compute this probability phi, because well, this is 1 over 2q times s times 1 minus the sum n from 0 to infinity 1/2 choose n times minus 4 pqs squared to the power n. This is just the expansion of the binomial, using the binomial expansion of the square root. And now you see that the term n equal to 0 is just 1, so it cancels with this one. So the series starts with n equal 1 term, so you have minus 1 over 2q times sum n equal to 0 to infinity of 1/2 choose n minus 4 pq to the power n times s to the 2n minus 1, where this minus 1 comes from this. So then what you see from this is that this generating function only contains odd powers of s, So this probability is non-zero only if n is odd. So if so from this you see that the probability that you get the first gain at an even number of games is equal to 0, and this is clear because of the parity of the random walk. Okay, and secondly, you can read what is this probability here. If you write down if you manipulate a little bit the binomial coefficient, then you find that phi 2n is equal to 0, and phi of 2n minus 1 is equal to 1 over 2n minus 1 times 2n, choose n, times pq to the power n divided by 2q. Okay? And okay, so you see that with generating function you find very easily the solution of this somewhat complicated problem. There is also another interesting observation that you get here. So let us look at this generating function computed in s equal to 1. So this will should give us the normalization. So okay, by the definition of the generating function. Or in other words, this will give you the probability that this gambler will ever make a gain, okay, for the first time, or will never ever make a gain. And okay, so this is 1 minus square root of 1 minus 4 p times, let me write q as 1 minus p, divided by 2 times 1 minus p. So you see that this 1 minus 4p plus 4p squared is 1 minus 2p squared. Under the square root, this is just 1, this is just 1 minus 2p absolute value divided by 2 times 1 minus p. And now you see that if p is less than 1, if p is less than 1, then this is 1 minus, so let's start with p larger than 1. If p is larger than 1, then this is negative, so you have that this is 1 plus 1 minus 2p, and it cancels with this, so you just get 1 if p is larger or equal to 1/2. Okay, so you get this, that this probability is correctly normalized. But if p is less than 1/2, instead here you get 1 minus 1 plus 2p, and so at the end you get p divided by 1 minus p, which is less than 1 if p is less than 1/2. So what happens? What happens is that with probability 1 minus p divided by 1 minus p, this event will never occur. So there will never be a gain. Okay. And so with the with probability 1 minus this, then there will never be a gain. And so this means that this is a probability distribution, normalized probability distribution, only if P is larger or equal than 1/2. If it is less than 1/2, it is not normalized. It's called a defective. It's called a defective probability distribution. Okay. So the other interesting thing that we can do with this generating function is to compute what is the expected time for that we have to wait for the first gain. And in this case, because it doesn't make sense for p less than 1/2, this event only occurs with a certain probability, it makes sense to compute the probability, the expected value of the waiting time for the first gain, conditional on the fact that there will be a first gain. And the way to compute this is just to take the first derivative computed in 1, but then you have to condition this on the fact that the waiting time will be finite, and this is given by just phi of 1. Okay, so if you do this calculation, which is very easy, what you find is that this is 1 divided by 1 minus 2p. So what you see from this is that if p is not equal to 1/2, then if there will be a gain, if you are going to gain sooner or later, then it's going to happen in a finite time, in a finite number of games, which is 1 divided by 1 minus 2p. Whereas if p is equal to 1/2, still for sure you know that there will be a gain, but the waiting time you have to wait for p equal 1/2 is infinite. Okay, this is similar to the first passage time that we have discussed. First return time of a random walk that we have discussed last time. Okay, so very good. So let's now use this technique to study retards of random walks. Okay, so I remind you that a retard to the origin is the event that S2n at time 2n is this event here. Okay. What is the probability of this event that we called U2n? Is it's just given by the binomial distribution. So in Sn you should have n steps up and n steps down. So this is just 2n, choose n, times p times q to the power n. Okay? It's just a binomial distribution. And then we can compute the generating function for this sequence, for this probability. So this is defined in the usual way, in this way. And if you do this calculation using again the manipulation of the binomial coefficients and the binomial theorem, then what you find is that this is 1 divided by square root of 1 minus 4 pq times s squared. Okay, again, the fact that when you expand this function, you only have even powers of s, implies that a retard to the origin only occurs, only can occur at even times. It can never occur at odd times. Okay, so this is very simple, and so if you want this, you can write it as -1 to the n, -1 choose n times 4pq to the n, and you can use this expression to get directly this result. Now let's consider the first return. Distribution. Okay. Again, I remind you, a first return to the origin is the event that S2n, so a first return occurs at time 2n if S2n is equal to 0 and Sk is different from 0 for all k that go from 1 to 2n minus 1. Okay? Okay, so how do we compute this first return? Again, in this case, we can use this calculation that we did here, because when we can compute the generating function of the probability that first return occurs at time n. Okay, so this is the probability that the first return occurs at time n. And this is again given by the expected value of S to the TF, to the first return. Okay? By definition. So we have to see from here what is the first return, and we can argue exactly in the same way as in this case. So if your first step is on the negative side, so then essentially the first return to the origin is given by just 1 plus the time for the first game, the waiting time for the first game. Okay, so this is 1 plus a first random variable which has exactly this distribution here if x1 is equal to -1, that occurs with probability q. Okay. Now what happens if the first step is on the positive side? Okay. So if the first step is on the positive side, it's exactly the same problem, but it's exactly a symmetric problem. So I will have to wait 1 plus the waiting time for the first loss. Okay. Okay, and this occurs with probability p. Okay. So what is the distribution of the waiting time for the first loss? So in this case, we are looking at the distribution for this event, where for the first time of the time for which the first time you hit -1. It's exactly the same problem as this. with the only difference that you have to interchange P and Q. Okay, because if you do the calculation, it's exactly the same calculation as before, but you have to interchange P and Q. Okay, so I can use this to compute the generating function of first return. And so with probability Q, I will have this one, 1 minus square root of 1 minus 4 PQS squared divided by 2Q times S. And because of this one, there is also an S. Okay, because the expected value of S to the 1 plus T is S times the expected value of S to the T. And then with probability P, I have exactly the same thing, but with P replaced by Q. So I have S times 1 minus the square root of 1 minus 4 PQS squared divided by 2P times S, because I have to replace Q by P. Okay? So you see that these things simplify, and I get a very simple expression, which is 1 minus the square root of 1 minus 4PQ times S squared. Okay? So this is the generating function for the first return times. In this general case where we have a biased random walk, a random walk which has a bias or a drift, okay? A drift either in the positive for p larger than 1/2 or in the negative direction. Okay, again, you can do the same calculation as before, and so let me write it here. So this is 1 minus the square root of 1 minus 4PQS squared. So f of 1, if you compute f in 1, then this is 1 minus, again, this is the square of 1 minus 2p. So it's 1 minus this, the absolute value of 1 minus 2p. So you see that this is less than 1 if p is different from 1/2. So it means that if p is not equal to 1/2, is different from 1/2, there is a finite probability, which is the absolute value of 1 minus 2p, that the random walk will never get back to the origin. Okay? And instead, with p equal 1/2, we recover, notice that when p is equal to 1/2, we recover the result that we have discussed last time, because it's becomes just 1 minus the square root of 1 minus s squared. And also, you can argue by the same argument as before, is that the expected value of the waiting time, the first return time, given that the first return times is finite, is equal to f prime of 1 divided by f of 1, as before. And you can do the calculation with this formula and find that this is 1 plus 1 over 1 minus 2p absolute value. So this tells you that if p is different from 1/2, the expected time to return to the origin is finite. So this suggests that if p is different from 1/2, either you come back to the origin after a finite number of steps, or you never come back to the origin. Whereas if p is equal to 1/2, then this diverges and we recover the result that we have discussed last time. Okay, so again, you can check that if you do the binomial expansion of this expression, you recover the result that we have discussed last time. So the expression for the probability f2n, again, this is a power, the power expansion of these only contains even powers of s, so this means that you can only return to the origin after an even number of steps. And f2n, if you take the binomial expansion, is just 1 over 2n minus 1, 2n choose n, times p times q to the power n. Okay? You see that when p and q are equal to 1/2, you recover exactly the expression that I gave you last time. Okay? Okay. Now, as we have said last time, this sequence and this sequence are related by a relation that that is the following. So that if you want to compute what is the probability of a return at time 2n, then this can be computed in this way. So you should return to the origin for the first time after 2n steps, and then in the remaining walk, you have to be back at the origin after 2n minus 2 new steps. Okay, so the idea of this is that if you are at the origin at 2n, there must be a first time for any walk that is at the origin at 2n. There must be a first time where the walk hits the origin, hits the axis, and then you have to be back at the origin after 2n minus 2 new steps. Of course, this nu can also be equal to 2n, okay, or it can also be equal to 0. Well, it cannot be equal to 0 because f of 0 is equal to 0, so it can be equal to 2n. So you get this equation. This equation, of course, is true only for n positive, okay? Because for n equal to 0, u0 is equal to 1, and f of 0 is equal to 0. Okay, so now the idea is that if you sum from n equal to 1 to infinity this equation multiplied by s to the 2n, okay, you do it both on the right hand side and on the left hand side, what do you get? Well, here you just get the generating function of u minus the first term, which is n equal to 0, which is 1. And on the other side, what do you get? You get the sum n from 0 to infinity of s to n, sum nu from 0 to n, f to nu, u to n minus 2 nu. So you see that you can split this s to the 2n into s to the nu and s to the 2n minus 2 nu. And then you can change these two sums and call these 2k. Okay, so and if you do this, you will find that you have a sum from k from 0 to infinity of u 2k times s to the 2k, and then you have a sum from nu from 0 also to infinity, because if this is n and k, here n nu, okay, here you are summing over all these integers, and when you make this change of variables, so k goes in this direction, and then you are summing from k from 0 to infinity. Nu, the sum of nu goes from 0 to infinity, and so this is f2 nu times s to the 2 nu. So this is equal to u of s times f of s. And what you see then, if you divide by u of s, what you find is that f of s must be equal to 1 minus 1 over u of s. And you see that this is exactly true. No, if you take 1, this is exactly 1 minus 1 over u of s. Okay? So this is a useful check for our formula, and whenever it is possible to check your formula, you should do it. And last thing I would like to discuss is the problem that we have discussed last time of last visit to the origin. Okay, so to the origin. Okay, so we have seen last time that for p equal 1/2, we had this arcsine law. This is a rather surprising result that the probability that the last visit to the origin occurs at a certain point between 0 and 2n is symmetric. So the problem we are considering is we have a random walk and of 2n steps, and we ask what is the last time k where the random walk was at the origin, and we would like to compute this probability that and as we said, this probability can be computed by the probability that the random walk is at the origin as 2k, and then times the probability that the random walk does not come back to the origin after in the remaining steps. Okay, Now this probability is actually the probability that for the random walk that starts from here, the first return is larger than 2n minus 2k. Okay? So the surprising thing that we saw last time is that by the lemma that for p equal to 1/2, this is equal to the probability that S2n minus 2k is equal to 0. So it's also the probability of a return at 2n minus 2k. Now for p different from 1/2, then this is not going to be the case. So let us, how do we compute this? Well, this is the generating function of the cumulative distribution of the first return time distribution. Okay, and you remember that there is a relation between the generating function of a probability distribution and the generating function of the cumulative distribution. Just remind you this relation. So the generating function of the cumulative distribution was 1 minus the generating function of the probability distribution divided by 1 minus s. Okay? So we can, if we know the generating function of the first return distribution, we can compute the generating function of the cumulative distribution by using that formula there. Okay, so how do you use generating function? Now we have two indices. So the idea is to introduce a function that, a generating function that depends on two variables. Okay, so which is the sum over n from 0 to infinity of and the sum from k from 0 to n of s to the 2n times z to the 2k of alpha 2n 2k. Okay, so this is a definition. So if we can compute this generating function, then we can look at the coefficients of different powers of s and z and figure out what this distribution must be. Okay? So this is the plan. Okay? Now, with the same trick as before, you can. So if you call this probability v of 2n minus 2k, then I can write this as the sum over n from 0 to infinity of the sum over k from 0 to n s to the 2n minus 2k times v of 2n minus 2k, which is this part here, times s times z to the power 2k times u 2k, okay, which is this part here, okay. Now, as before, we can change variables in this sum and do the same argument as before. So what we find is that this is u of s, the generating function of u, times the generating function of this sequence here. But this is the cumulative distribution of the first return time. So this is u of s times 1 minus f of s divided by 1 minus s squared. So why s squared and not s? Because f of s only contains even terms in s, even powers of s. So if you redo the same argument that led to that, then you find that in that case there are no odd powers, and so the analogous relation is this one. Okay. Okay. So now, given that we have the expression for u and the expression for v, so v is computed in s, but u is computed in s times z. Okay. Okay, because of this. Okay, so we have we can write down an explicit expression for this double generating function, and this reads so 1 over the square root of 1 minus 4 pq times s squared times z squared times 1 minus, well, 1 minus f of s is just the square root of 1 minus 4 pq s squared divided by 1 minus s squared. Okay. Okay, so now first thing that we can check is so first thing you notice that when I set z equal to 1, what I'm doing, I'm checking the normalization. So I'm checking the normalization of this probability over k, okay? Because a of s and 1 is equal to the sum over k, say sum over n 0 to infinity of the sum over k from 0 to n of alpha to n to k times s to the 2n. Okay. Now, if this probability is normalized, then this is equal to 1. And what I should expect if the probability is normalized is that this is just a geometric series of s to the 2n. So this is just 1 over 1 minus s squared. Okay. So, and indeed you see that if you set z equal to 1, then this exactly cancel with this. We just get 1 minus s squared. So we get that this probability distribution is correctly normalized. Now, what happens if I compute now the first derivative, the partial derivative of this with respect to z, and set z equal to 1. Now, if I do this, then what happens is that I get a 2k here. Okay? So this essentially gives me the sum over n from 0 to infinity of s to the 2n times the expected value of the time, let me call it L, of the last visit. So this tells me what is the last time, what is the expected, if I look at this function here as a function of s, and if I look at what is the coefficient of s to the 2n, then this is going to be the expected time of the last visit to the origin of a random walk between 0 and 2n. Okay? So let's do this first derivative. So you see the first derivative only involves this first term here. And so if you do this, and you can do this as an exercise, so this is the expected value, well, conditional on the length of the random walk to be 2n. You find that the last visit of a random walk of 2n steps, the expected value is equal to 4pq divided by 1 minus 4pq times 1 minus 4pq dn. Find this expression, and what does this expression tell you? So if p, so if p is equal to q is equal to 1/2, then you have a 0 here and a 0 here. So you have to use L'Hopital rule, and essentially this gives you 4pq, which is 1. This gives you exactly equal n. Okay. But if p is different from 1/2, then this term here is less than 1. So for large n, this is exponentially small, and essentially the expected time of the last visit is finite. Okay, so for p, which is different from 1/2, the last visit to the origin, you expect that the last visit to the origin will be close to the origin. Okay, and this is very different from what happens when p equals 1/2, where the last visit was as likely to be close to the origin as close to the end, as we saw by the arc sine law. You can get more information from this distribution. In particular, you can compute this, you can expand this in powers of z and s, and find what is the general expression for this. But I think this information already gives us a lot of insight of what happens to the arc sine law when these random walks have a drift. Okay, when p is different from 1/2. So the last thing I want to mention is that yes, this particular equality that we had for p equal 1/2 meant that this generating function v of s should have been equal to u of s, and you see that this is true because this is the generating function v of s, and when the generating when p is equal 1/2, then this is exactly 1 over the square root of 1 minus s squared, which is exactly equal to the generating function of u. Okay? So, but this is only true for